As of now, we design, suppose if I have a n number of flip-flops, so the maximum mode that is possible is 2 to the power n, and that is the m. Okay, this is the maximum mode, but this is also possible that the mode can be even less than 2 to the power n. This is also possible. Okay, just now we just design with the help of 3 flip-flops, we designed mode 5 counter. Okay, so this was possible. But suppose if I have to follow some procedure, like how we can do that. So in reality, suppose if I have a mode m counter, and from this mode m counter, or for like mode 2 to the power n counter, if I have to design some mode m counter, so we need some decoder circuitry as well. Okay, some logic gates are required to clear so that it can reset to the 0. Okay, so suppose if I have to make some modulus m counter, in that case, what kind of procedures I have to follow? Okay, so that we should know. So these are some of the procedures that we need to follow to design mod m asynchronous counter. Okay, I'm not going into more detail. We'll take the example, and then you will get to know about what the procedures we are going to follow. Okay, so reading the procedure is not important, but the important thing that what we can, I just told you, the maximum mode that is possible is less than or equal to the power n. Okay, and this is what the process is. Suppose, what is the flow? What this procedure is saying? Suppose I have a counter, okay, having the n bits. So if there is n bits, so maximum mode that is possible is 2 to the power n. So this is the maximum mode which is the possible. Here CP is the clock pulse. Okay, now because I have to reduce the mode with the help of this counter, so I need some additional circuitry, and those additional circuitries are controlled by the output of this counter. So let us assume the output of these counters are Q0, Q1, and so on. So those extra circuitry or the decoder circuitry are controlled with the help of output of this counter. Okay, so we need some combinational logic circuit, and that is giving some output Y, and this output Y is connected to the clear of the counter. This is what we have already done. Okay, but this is what the pictorial representation of mod m asynchronous counter is. Okay, so this is how we can design it. So let us try to see how we can do this by following the procedure. Okay, as of now we have not followed any of the procedure. We just checked which of the state is not desirable, and accordingly we just connected a logic gate that can clear the output. Okay, but if I have to follow some procedure, then how it could be done? Let us try to see. Let us take an example and try to make it. Design a mod 5 asynchronous counter and also draw the timing diagram of the sequence. Okay, as of now we have already designed this mod 5 counter, but without following any procedure. But let us try to follow the procedure and try to design the mod 5 asynchronous counter. Okay, so what the first step is? First step is just to check what are the different sequences which are possible. So the total sequences which are possible here is 0, 0, 0 to 1, 0, 0. So the initially it will start from 0, 0, 0, then it will move to the 0, 0, 1, 0, 1, 0, 1, 0, 0, and 1. Then again it will be preset to 0, 0, 0. Okay, so this is the sequence which we are going to follow. Now let us try to see what is the output of all those things. Okay, so let us try to see the sequences. I am considering this Q2 is the MSB and Q0 is the LSB. In that case, because the sequence that will start from 0 and that will reach up to 1, 0, 0, and then after it will be preset to 0, 0, 0. So let us see how it could be done. So the counter will start from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So this is the sequence which are possible, but the Y is connected to the clear. Okay, so and to clear the flip-flop, I need to generate this y at logic 0. Y should be logic 0 to clear it. Okay, so if the first stage 0 0 0 is there, so I don't need to clear it because I have to move to the next stage. Okay, so the y should be 1 at this point. Okay, so let me change the color. So y should be 1, and if y is equal to 1, it will not clear the flip-flops. Now the next clock pulse will come like 0 0 1. 0 0 1 is also the valid state. Okay, so if at this valid state y should be 1, so that it will not clear the flip-flop. 0 1 0, this is the valid state. 0 1 1, this is the valid state. 1 0 0 is the valid state. Then after 1 0 0, it should move to the 0 0 0. So the y means which is connected to the clear pulse, that must be 0. This y must be 0. When 1 0 0 comes, at this stage y should be 0, so that it can clear all the flip-flop and that can reach to the 0 0 0 again. Okay, so this is the required thing, this is the important thing. Okay, so y will be 0 when 1 0 1 will come. Okay, and then after, these are the don't care state, because these two states will not come, so it does not matter what is the status of y. Okay, so this is the truth table that we got after this one. Once we are ready with this truth table, what I have to do, I have to simplify the k map for y. Okay, so the k map for y will look like this one. So let us try to see here. It will be like 1 1 1 1, and then 4 is also 1, 5th is 0, 6 is don't care, and this is don't care. Okay, so the k map for y will be like this. Now let us try to make the pairing of it. How we can make the pair? So one pair is possible, like one chord is possible here. So this is the one chord which is possible. Second one is, can anyone tell me which is the next pair that is possible? Anyone?
Sir, 0 4
0 4
3 2 7 6
0
4
6 4
4 2 6
0 4 2 6. Perfect. 0 4 2 6 is the right one. Okay, because see here, here we have a don't care, so we can use this in the pairing. Okay, so the first thing that is very important is like we have to make the highest possible pairing. Okay, so the one possibility of this pairing is like this chord is also possible. Okay, so if this chord is possible, then what is the output which we are getting here? So the output is like y is equal to, from this green quad, I will get the Q2 bar. Okay, and then plus from this one, I will get Q0 bar. Okay, so the Q0 bar plus Q2 bar is the final expression. Okay, now let us try to design the circuit. Like this y should be connected something like Q2 bar plus Q0 bar. So what I can do here, this is the Q2, here Q0, and here I have a Q2. So what I can do, I can simply use one AND gate, one OR gate that can use the Q0 bar and the Q2 bar. Okay, and that will be connected to the y, and this is how the logic will look like. Okay, so this is one of the possibilities that we can have. Okay, so this is one of the possibility. Second possibility could be like, yes, of course we can use one OR gate and the Q0 bar and the Q0 bar and the Q2 bar is connected. Yeah, Q2 is here. So the Q2 bar should be connected. Q0 bar and the Q2 bar should be connected, and that should connect to the output Y. Okay, so this is how we can make the mode 5 counter. Another possibility could be like if we try to simplify this expression is nothing but this looks like Q2 dot, yeah, just apply the De Morgan's theorem. The Q2 dot Q bar whole complement. Okay, so either I can use, so if I am using this one, so I need OR gate, and if I am using this one, then I need NAND gate. Okay, so the question could be like design a mode 5 counter or synchronous up counter with the help of a mod 8 counter and a NAND gate. So in that case, I have to use this one. And if OR gate is given, then I have to use the upper one. Okay, so both are possible. Either I can use the OR gate or I can use the NAND gate. Okay, and both will solve the purpose. That's not a problem. Okay, but the question is which of the logic is recommended? Because the NAND gate is recommended because the NAND gate is the universal gate. Okay, so this can be utilized some here and there as well. So prefer to use the universal gate, that will help you. Okay, so this is how the this can be designed. Mode 5 counter can be designed. Okay, if anyone has any doubt, you can ask the question here. Okay, so both are the possible, both possibilities can be done. Okay, yeah, so here we have some tutorial questions. Design a BCD up asynchronous counter. BCD up asynchronous counter means what? The counter that starts from BCD means 0 to 9, right? So it will start from 0 0 0 0 and it will run up to the 1 0 0 1. So total number of flip-flop requirement will be 4. So 4 flip-flops are required, and after this 1 0 0 1, it should preset to 0. Okay, so the invalid states are 1 0 1 0. So once it reaches to the 1 0 1 0, it should clear the status of flip-flops. So this is how the BCD counter will look like. Similarly, you can also make the BCD down counter, mode 4 up counter, and the mode 4 down counter. So this is the tutorial questions that you have to do at home. Okay, these are some homework. Okay, yeah, these all are easily doable. Just follow the procedure back which we followed in the previous slide, and then you can do it.